Hello and welcome to this A-level chemistry multiple choice exam question walkthrough. Feel free to download the questions from the link in the description, have a go at them yourselves, and then watch this video to see how you got on. Which cannot function as a Bronsted-Lowry acid? Well, a Bronsted-Lowry acid is defined as being a proton donor, whereas a Bronsted-Lowry base is a proton acceptor. And since we've been asked which of these cannot function as a Bronsted-Lowry acid, we're looking for the one that cannot donate a proton, or to put it differently, cannot donate a hydrogen ion. And so we need to look at each of our options. Well, the first one is the ethanoate ion. And this is in fact the correct answer because the ethanoate ion does not have any hydrogen ions that it could donate. Hydrogen atoms connected to carbon atoms cannot readily be lost, so it is not able to act as a Bronsted-Lowry acid. Whereas each of the next three, they have a hydrogen ion that could be removed in the presence of a Bronsted-Lowry base, and so all three of them could act like a Bronsted-Lowry acid, and so A is correct. A strong acid, H2X, dissociates in aqueous solution, and we've been shown the equation for this dissociation here. What is the pH of a 0.020 mole per decimeter cubed solution of this acid? Well, first of all, we need to recognise that the pH equation says that pH is equal to negative log of the hydrogen ion concentration, and so that's going to be the final thing that we do. We just need to quickly check what information we've been given. We've been given the concentration of the acid, in other words, H2X. Additionally, it is a strong acid, which means it will fully dissociate. In other words, however many molecules of the acid we have at the beginning, it will all dissociate into the component ions. And we need to recognise that this acid is diprotic, which means that it produces 2 hydrogen ions per molecule. So the acid concentration is 0.02, but the hydrogen ion concentration will be double that, in other words, 0.04. And so then we need to take the negative log of 0.04, which gets us 1.3979. And then when we look at our 3 significant figure options to 2 decimal places, that is 1.40. And so B is correct. This question is about the reaction between propanone and an excess of ethane 1,2-diol, and the equation is given here. Here is propanone, and here is ethane 1,2-diol. In a typical procedure, a mixture of 1 gram of propanone and 5 grams of ethane 1,2-diol and 0.1 grams of benzene sulfonic acid, here is its formula, is heated under reflux in an inert solvent, and we're told that benzene sulfonic acid is a strong acid. The benzene sulfonic acid is not present in the equation, and we can therefore assume that it is a catalyst. If 0.1 grams of the strong monoprotic acid, benzene sulfonic acid, was dissolved in 100 cm cubed of water, the pH of the solution would be. So this is kind of a trick question because we've been given a lot of decoy information above the actual question. In fact, really all we need to look at is this bit towards the bottom. And so ultimately we've been asked for the pH of the solution. pH is negative log 10 of the hydrogen ion concentration, and so we need to work out what the hydrogen ion concentration is. Well, it's a monoprotic acid and it's a strong acid. So a strong acid means it will fully dissociate. So this benzene sulfonic acid will dissociate into these 2 ions, and it's monoprotic, which means that the moles of the benzene sulfonic acid will be equal to the moles of the hydrogen ions that are produced. So it'll be 1-to-1. And so what we have to do is we have to work out the moles of the benzene sulfonic acid by doing mass over mR, and this will give us the moles present in 0.1 grams, and then we have to divide that by the volume to get a concentration of benzene sulfonic acid. And so the benzene sulfonic acid has an MR of 77 for the C6H5 region. That's quite useful to remember C6H5 has got an MR of 77, but you can of course work it out, 12 times 6 and 5 times 1. Sulfur is 32.1, Oxygen is 16 multiplied by the 3, and then an extra 1 for that last hydrogen. So that gives us an MR of 158.1 grams per mole. We've got the mass of 0.1 grams, and so moles is 0.1 divided by 158.1, which gets us 6.325 times 10 to the minus 4 moles. Now we want a concentration, and so since moles is concentration times volume, concentration is moles divided by volume. The volume needs to be in dm cubed. Currently it's in cm cubed, so we need to divide that by 1,000, and that's 0.1 dm cubed. So the concentration is 6.325 times 10 to the minus 4 divided by 0.1, which is 6.325 times 10 to the minus 3. That's the benzene sulfonic acid concentration, which will be the same as the hydrogen ion concentration because it is a monoprotic strong acid. So we just need to do negative log of 6.325 times 10 to the minus 3, and that gets us 2.1989 or 2.20 to 2 decimal points, and so C is the correct answer. A solution of sodium ethanoate has a pH of 8.91 at 25 degrees C. The hydrogen ion and hydroxide ion concentrations in this solution are... Well, the first thing that we need to recognise is if the pH is 8.91, we can do 10 to the power of minus 8.91 to get the hydrogen ion concentration. And that value, once you put that into your calculator, gets us a hydrogen ion concentration of 1.23 times 10 to the minus 9. And so that means that we can rule out A and B because they have the wrong hydrogen ion concentration. And so now we need to decide which of these two hydroxide ion concentrations is correct. Well, the significance of that temperature is that if it's 25 degrees C, the value for Kw, the ionic product of water, is going to be 1 times 10 to the minus 14, because that's just a fact that you need to know about 25 degrees C temperature. And Kw is the product of the hydrogen ion concentration and the hydroxide ion concentration. And so we need to maybe just inspect these numbers and say, right, well, if the hydrogen ion concentration is 1.23 times 10 to the minus 9, what can we multiply that by to get 1 times 10 to the minus 14? And you can actually just inspect the number for the hydroxide ion concentration. If we do 1 multiplied by 1.23, we're not going to get 1. Doesn't matter about the standard form. 1 multiplied by 1.23 is 1.23. And that will give us the incorrect value for Kw at 25 degrees C. So that means that C has to be the incorrect answer. And so D has to be the correct answer, given that we've ruled out the other 3. But if we just check the maths of this, the hydrogen ion concentration, 1.23 times 10 to the minus 9, multiplied by the hydroxide ion concentration, 8.13 times 10 to the minus 6, does indeed round to 1 times 10 to the minus 14, mole squared dm minus 6. And so D is correct. The pH of a 0.001 moles per decimeter cubed solution of sodium hydroxide at 25 degrees C is... Well, if we're asked to work out a pH, that means we need to use pH equals negative log 10 of the hydrogen ion concentration. So in order to calculate pH, we need to find that hydrogen ion concentration. We're using a strong base here, sodium hydroxide. That means it will fully dissociate in solution. And so we need to use the Kw expression. Kw, the ionic product of water, is equal to the hydrogen ion concentration multiplied by the hydroxide ion concentration. And since we've been told that it's 25 degrees C, that means that the value for Kw is 1 times 10 to the minus 14. And so we can substitute that into the Kw expression. And so, since the strong base concentration is 0.001 moles per decimeter cubed, that will be the same concentration for the hydroxide ions. And so we can rearrange this equation, and the hydrogen ion concentration will be 1 times 10 to the minus 14 divided by 0.001. which gets us 1 times 10 to the minus 11. And then when we take the negative log of that value, we get a pH of 11.00. And so B is the correct answer. The pH would be 11. In which of the following reactions is the role of the reagent stated correctly? In A, is titanium oxide an oxidizing agent? Well, oxidation is the loss of electrons, and so the oxidizing agent causes that loss by accepting electrons. And so if the element is accepting electrons, its oxidation state will be going down. In titanium oxide, the oxidation state of the titanium is +4 because the oxygens are each -2, and there are 2 of them. And then in the products, the titanium has become titanium chloride, and the titanium is still +4 because each of those 4 chlorides is -1. And so titanium oxide is not the oxidizing agent here. In B, is nitric acid a Bronsted-Lowry acid? Well, a Bronsted-Lowry acid is a proton donor. Has the nitric acid donated a proton? Well, at the beginning of the reaction, the nitric acid has 1 proton. And then at the end of the reaction, the nitric acid has got a second hydrogen atom, which means actually it has accepted a proton, and so it has behaved as the Bronsted-Lowry base, which means that the sulfuric acid must be the Bronsted-Lowry acid. In C, is aluminium chloride a Lewis base? Well, a Lewis base is an electron pair donor, which it uses to form a coordinate bond to an electron pair acceptor, the Lewis acid. Well, aluminium chloride has actually only got 6 valence electrons because aluminium is in group 3 and it's bonding with 3 chlorine to make the almost full shell. But actually aluminium chloride is quite stable in this arrangement. But since it's not got any lone pairs at all, it can't be acting as a Lewis base. And in fact, the chlorine which joins it as a chloride ion is the Lewis base, and the aluminium chloride, specifically the aluminium from within it, is going to accept that pair of electrons. And that means that D must be the correct answer. Carbon monoxide is a reducing agent, and that makes sense because reducing agents are electron pair donors, or electron donors, I should say. And so the carbon begins with an oxidation state of +2, and it finishes with an oxidation state of +4, which means it must have lost 2 electrons, in fact, which it has donated to the nitrogen atoms. And so D is the correct answer. The carbon monoxide is a reducing agent because the carbon has donated electrons. The equation and rate law for the reaction of substance P with substance Q are given below. And here is the rate equation, which is of particular importance here. Rate equals K, concentration of P to the power 2, multiplied by the concentration of hydrogen ions. Under which one of the following conditions, all at the same temperature, would the rate of reaction be slowest? And you can see we've got 4 situations, 4 different concentrations of P in moles per decimeter cubed, and P is here in the rate equation, but we've got 4 different pHs. And so what we're going to be needing to do here is convert those pHs into hydrogen ion concentrations. And the reason that we need to do that is that the rate is proportional to the concentration of P squared multiplied by the hydrogen ion concentration. And since pH is negative log 10 of H plus concentration is 10 to the minus pH. And so 10 to the minus 0 is 1, 10 to the minus 2 is 10 to the minus 2, and then we've got 10 to the minus 3 and 10 to the minus 4 for the hydrogen ion concentrations. And so what we need to do now is we need to find the product of those terms. They won't be equal to the rate, but they will be proportional to the rate. And since we're trying to find out which one of these will be slowest, what we're looking for is the one where the product of these terms is the smallest. And so we need to do for A, 0.1, that's a concentration of P, squared multiplied by 1. And so that gets us 0.01, or 10 to the minus 2. And then for B, we've got 1 squared multiplied by 10 to the minus 2. So that's 10 to the minus 2. For C, we've got 3 squared multiplied by 10 to the minus 3. And this gets us 9 times 10 to the minus 3. And for D, we've got 10 squared multiplied by 10 to the minus 4. And that comes out at 10 to the minus 2. And so since the product of 3 of these is the same number, 10 to the minus 2, C is the odd one out. Its number is smaller, 9 times 10 to the minus 3. That means that this is the smallest rate, and so C is the correct answer. It would be the slowest reaction. Equal volumes of two solutions, each with the same concentration, are mixed together at 298 Kelvin. Which two solutions, when mixed, form a solution with a pH of greater than 7? In A, we've got methanoic acid and potassium methanoate. Methanoic acid is a weak acid, and potassium methanoate is a salt of that weak acid. So these two chemicals actually won't react together at all. What we've got is a buffer mixture, and it's a weakly acidic buffer because methanoic acid is a weak acid, and so its pH will in fact be less than 7. And so A is not the correct answer. In B, we've got potassium hydroxide, a strong base, and ethanoic acid, a weak acid. And so those will obviously neutralise each other, but what they will produce is water, of course, and potassium ethanoate. Potassium ethanoate, whilst it is a salt, it doesn't quite have a pH of 7 because the ethanoate ion can accept a proton in the presence of water, and so therefore it will be a weak base. And so this is the correct answer. Its pH will be slightly greater than 7. In C, we've got a weak base, ammonia, reacting with a strong acid, hydrochloric acid. And so when they react together, they will produce ammonium chloride salt. Now, ammonium chloride is actually weakly acidic, and so the pH will be less than 7. It's acidic because the ammonium ion can donate a proton when dissolved in water. And so the pH would be less than 7 for this one. And then finally, we've got ammonium chloride mixed with potassium chloride. So we've got two salts. And so potassium chloride has a pH that will be about 7 because neither of these will interact particularly with water. However, ammonium chloride is going to be weakly acidic because the ammonium ion can donate a proton. And that means that this will also have a pH slightly less than 7. And so B is the correct answer. Which statement about pH is correct? The pH of a weak base is independent of temperature. Well, all bases accept protons, and weak bases will only partially accept protons, which means that this reaction will be an equilibrium. When the proton is accepted, this is the formation of a new attraction, so that will be exothermic. And then when the conjugate acid falls apart and remakes that weak base, this is a dissociation, so that will be endothermic. And so that means that if we increase or decrease the temperature, the equilibrium will shift in the endothermic or exothermic direction to compensate for that. So A is not correct. At temperatures above 298 Kelvin, the pH of pure water is less than 7. Well, water can dissociate into H plus and OH minus ions, and like all dissociations, this is going to be endothermic, and therefore the reverse reaction will be exothermic. According to Le Chatelier's principle, if we increase the temperature, the equilibrium will shift in order to decrease that temperature. And so the equilibrium is going to shift in the endothermic direction, which is to the right. Therefore, increasing the temperature is shifting the equilibrium to the right. The hydrogen ions are on the right-hand side, so more hydrogen ions will be made. And importantly, the concentration of hydrogen ions will increase. And since the pH is the negative log of the hydrogen ion concentration, there will be a larger hydrogen ion concentration. And that will mean that there will be a lower pH. And so the pH of pure water at 298 Kelvin is 7. And so if that pH is going down, then the pH will now be less than 7. And so this is a true statement. C is incorrect because the pH of nitric acid with a concentration of 2 moles per decimeter cubed is negative log 2, which is minus 0.3. D is not correct because the pH of the same concentration of a diprotic acid is going to be less than the equivalent concentration of a monoprotic acid because there will be double the hydrogen ion concentration and so therefore a lower pH. A saturated solution of magnesium hydroxide, MgOH2, contains 0.1166 grams of magnesium hydroxide in 10 dm cubed of solution. In this solution, the magnesium hydroxide is fully dissociated into ions. Which one of the following is the pH of a solution of magnesium hydroxide containing 4 times 10 to the minus 5 moles per decimeter cubed of hydroxide ions at 298 Kelvin? And we're told that the value of Kw is 1 times 10 to the minus 14 mole squared dm minus 6 at 298 Kelvin. Well, this is quite a sneaky multiple choice question because they've given you quite a bit of information that you don't need that is sending you down a path that you shouldn't follow. The crucial bit of information is the last two things that they've told us. They've told us the value of Kw, which means we're going to need to use the Kw expression, where Kw equals H plus concentration multiplied by OH minus concentration. And they've told us the value of Kw, and they've told us the value for the hydroxide ion concentration, 4 times 10 to the minus 5 moles per decimeter cubed. And so that means that we need to work out what the hydrogen ion concentration is before we can calculate the pH. And so we substitute in the value for Kw and the value for the hydroxide ion concentration, and we're left with the expression 1 times 10 to the minus 14 is equal to the hydrogen ion concentration multiplied by 4 times 10 to the minus 5. Therefore, the hydrogen ion concentration is 1 times 10 to the minus 14 divided by 4 times 10 to the minus 5, which gives us a value of 2.5 times 10 to the minus 10. And since pH is negative log 10 of the hydrogen ion concentration, we need to do negative log 10 of 2.5 times 10 to the minus 10, and that gets us a pH of 9.6. And so A is the correct answer. This question is based on the reactions and compounds shown in the scheme below. A 0.1 moles per decimeter cubed solution of X, which is this compound on the right-hand side, is found to have a pH of 2.50. The value for Ka in moles per decimeter cubed is. And so on this occasion, we've been given a reaction scheme, but actually all we're doing is looking at compound X on the right-hand side, which is some kind of weak acid because we've got this carboxylic acid group at the top. When we've been asked to work out a Ka, there are only two ways to do this. One, we have to use a pKa, but we haven't been given a pKa, and the other is to work out the Ka from the Ka expression, and so that's what we'll have to do here. So the Ka expression in general for any weak acid is Ka equals H plus concentration multiplied by A minus concentration divided by HA concentration. And we're using A as a generic, the rest of this acid, so the conjugate base that forms once that proton is donated. Now for a weak acid, we're allowed to assume that the hydrogen ion concentration is equal to the conjugate base concentration, so that's the A minus concentration. And therefore, Ka equals H plus squared divided by HA. And since pH is negative log of H plus, we can therefore calculate the H plus concentration by doing 10 to the minus pH on our calculator. So therefore, H plus concentration is 10 to the minus 2.5, which gets us 3.162 times 10 to the minus 3. Then if we plug that into the Ka expression on top, and the HA, which is this value 0.1 moles per decimeter cubed, onto the bottom, we get a value for Ka as 9.998 times 10 to the minus 5. Now that isn't any of our options, so we need to do some rounding to 2 decimal points, and that comes out at 1.00 times 10 to the minus 4. And so C is the correct answer. The diagram shows a pH curve produced by adding a strong alkali to a weak acid. Which point on the curve represents a solution that can act as a buffer? You can get weak acid buffers or weak base buffers, and so our first job is to decide which of those we're aiming for. Since we've got a strong alkali, we're not going to have a weak base buffer. It must be a weak acid buffer, and we're working with a weak acid, so that looks promising. To have a weak acid buffer, you need to have some weak acid and one of its salts. So you need both of those components in order for it to be a weak acid buffer. pH curves are generated by having something in the conical flask. We've got a low pH at the beginning, so we're going to be starting with a weak acid in our conical flask and adding alkali to it, this strong alkali. So in situation A, we haven't started our titration. We've added 0 mils of our alkali, so we've only got the weak acid in our conical flask. So we can rule out A because we only have the weak acid. And then after we add some alkali, we'll neutralise some of that acid, but not all of it. And so what we'll have in situation B is we will have a salt of that weak acid, but we haven't reacted all of that weak acid, so we've still got some of it left over. So B is actually the correct answer because we've got the two components needed for a buffer. We can also see that it's correct because that pH is pretty constant. Even though we are continually adding alkali to our mixture, the pH change is being resisted, which is showing that there is a buffer solution. C is incorrect because C is the equivalence point, and at that point all of the acid has been neutralized by the alkali, so we only have got salt at point C. Whereas D, we've got an excess of alkali, so at that point we will have some strong alkali and we will have majority of our salts. And so B is correct. 2,4,6-trichlorophenol is a weak monoprotic acid with a Ka of 2.51 times 10 to the minus 8 moles per decimeter cubed at 298 Kelvin. What is the concentration in moles per decimeter cubed of hydrogen ions in a 2 times 10 to the minus 3 moles per decimeter cubed solution of 2,4,6-trichlorophenol at 298 Kelvin? When we're answering a question like this, we can take some shortcuts, so we don't need to draw out the structure of this weak acid, we can just refer to it as HA. And it's an acid, which means it's going to dissociate into H plus ions and A minus ions. It's a weak acid, so that means that dissociation is only partial, so we use the reversible reaction symbol, and it's monoprotic, which means that when it dissociates, we just produce the one H plus ion per dissociation. Now, we've been given a Ka value and asked to calculate a hydrogen ion concentration, so that means that we need to use the Ka expression. Ka equals H plus concentration multiplied by A minus concentration divided by HA concentration, which is the undissociated acid concentration that we've been given there of 2 times 10 to the minus 3. For a pure monoprotic weak acid, for every molecule that dissociates, we produce one hydrogen ion and one A minus ion. So that allows us to make the assumption that the H plus concentration is equal to the A minus concentration. Therefore, Ka can be calculated by H plus concentration squared divided by the HA concentration. This means that if we sub our values in, we get 2.51 times 10 to the minus 8 is equal to the hydrogen ion concentration squared divided by 2 times 10 to the minus 3. And then when we rearrange that, we get H plus concentration squared is 2.51 times 10 to the minus 8 multiplied by 2 times 10 to the minus 3, which gives us 5.02 times 10 to the minus 11. And so to find the hydrogen ion concentration, which is what we've been asked to do, we just need to square root that value. And so we get an answer of 7.09 times 10 to the minus 6. And so B is the correct answer. Which is the concentration of sodium hydroxide in moles per decimeter cubed that has got a pH of 14.30? And we've been told that the Kw is 1 times 10 to the minus 14 at 25 degrees C or 298 Kelvin. When you've been given the Kw value, it's a pretty big signal that you're going to be using the Kw expression, where Kw is H plus concentration multiplied by OH minus concentration. It's important to note that this expression has the hydroxide ion concentration, not the sodium hydroxide concentration, but on this occasion they are the same thing since there is one hydroxide ion in one sodium hydroxide. If it had been something like magnesium hydroxide, that would have been more complicated because it wouldn't have been a 1-to-1 ratio. We've got the value for the pH of 14.30, and so since pH is negative log of H plus concentration, the H plus concentration is 10 to the minus pH, so 10 to the minus 14.3, which gives us 5.012 times 10 to the minus 15. And so the Kw, 1 times 10 to the minus 14, is equal to 5.012 times 10 to the minus 15 multiplied by the hydroxide ion concentration. And so therefore the hydroxide ion concentration is 1 times 10 to the minus 14 divided by 5.012 times 10 to the minus 15, and then that gives a value of 1.995 moles per decimeter cubed for the hydroxide ion concentration. And that rounds to 2 decimal points to 2.00 for the hydroxide ion concentration, which is the same as the sodium hydroxide concentration, and so D is correct. Which indicator should be used in a titration to find the concentration of a solution of methylamine using 0.01 moles per decimeter cubed of hydrochloric acid? Well, methylamine is a weak base and hydrochloric acid is a strong acid. And so without doing any calculations, we know that the pH at equivalence is actually going to be less than 7. And that's always the case in a strong acid, weak base. To get a pH of exactly 7 at equivalence, we would need to have a strong and a strong or a weak and a weak. We actually can do better than that because we know what the concentration of the hydrochloric acid is. It's 0.01 moles per decimeter cubed. And so that means for the acid, the pH is going to be 2. Now, obviously, as you do this titration, that pH is going to change. It's going to go up from pH 2, and at some point it is going to be neutralized. But the pH at the equivalence point is going to be less than 7, but clearly it's going to be much greater than 2 because that pH will have risen gradually. And so when we're selecting an indicator for the titration, we need to pick an indicator whose pH range will align with the sharp change in pH that you always get at equivalence. And so it needs to align with that vertical region of the pH curve. We can't guarantee that thymol blue will work because the pH range is too low. We're going to be starting at a pH of 2, and we can't guarantee that we will have got to the equivalence point at 2.8. And so thymol blue will miss the equivalence point. Bromophenol blue, that looks like the best bet because the pH range change of between 3 and 4.6 seems like it's going to align with this equivalence point towards the bottom part of this pH curve. Phenol red is probably too late. We can't guarantee it without knowing the concentrations, but it's probably going to miss it because its pH range is higher than the pH at equivalence, and therefore phenolphthalein is even less appropriate because its pH change range is higher still. And so bromophenol is the most appropriate indicator, and so B is correct. Okay, that's the end of this video. See you again soon.